All right, this video is going to focus on solving a related rate problem. Okay, and these 6 steps, these would be the 6 steps to solve any type of related rate problem. Now, today's lesson or this video will focus mainly on some of the easier types. All right, we'll look at some area and volume type questions, but they do get more difficult as we go on. But realistically, you can use these 6 steps to solve any. It doesn't matter how simple, how complex, this is what you're going to do. So a lot of times a diagram will help. Today, a diagram is probably not necessary. List what's given in differentiation notation. dA over dt, that would be the rate at which the area is changing with respect to time. dV over dt, that's the rate at which the volume is changing. Okay, a lot of times you can tell by the units. So with this here, number 2, all right, in a question, if you have like linear units, okay, say you have something like 3 centimeters, well, that's probably going to just be like a length, or it could be the radius equals, or so on, okay, or the width of something, and you could use x. But if it's just linear units, you're talking a side length or a radius. If it's square units, like say it was 9 centimeters squared, or let's say it was 25 inches squared, something like that. Well, that would be an area. And if it's units cubed, remember, like say it was 27 cubic centimeters, that would be volume, or let's say we had 125 inches cubed. I'll change this to inches just so you can follow. Okay. Now, what you'll notice in today's lesson is that you'll see things like the following. It might say something like 9 centimeters per second. Sorry, 9 centimeters squared per second. Well, that's not an area, okay, because it's centimeters squared, but there's a unit of time after. That's actually a dA over dt, the rate at which the area of the figure is increasing. So let's be careful of our units. If you had something like this, 27 cubic centimeters per minute, right? That would be the rate at which the volume of the figure is increasing. So it's important to watch your units when you're doing these questions. And then list what's to be found, find an appropriate equation. This part's important too. Okay, that's not always obvious. Today it will be fairly obvious because we're going to be talking about the area of a circle, the area of a rectangle, the volume and area of a sphere or some specific geometric shape. Differentiate both sides with respect to time. Okay, that's what we learned how to do yesterday or in the last lesson. And then we're just going to sub in our known values and solve for the unknown. Okay, so here we go. The length of a square is 4 meters and is increasing at a rate of 125 or 1.25 meters per minute. How fast is the area of the square increasing? So first of all, the length of the square. So I like to write down my given information. Again, I don't need to draw a diagram for this. It's just going to be a square. Right? You could. And the length would be 4 meters. Okay, all side lengths would be 4. So I know that L is 4. Now this here confuses some people. All right, check it out. That's the rate at which the length is increasing. Notice the units. It's a linear unit, so it's going to be a length, but it's per unit of time. So in differentiation notation, that would be my dl over dt. And how fast is the area of the square increasing? Now, again, does it ask for the area? Does it say what is the area of this? square? No, it doesn't ask for the area. It asks for the rate at which the area is increasing. That's what I'm looking for. Okay. I got to figure out a formula that relates the length of a square to its area. Well, that's pretty simple. It's just the area of a square. Now, a lot of times you'd say the area of a rectangle's length times width. When it's a square, both length and width are the same. So I end up with this. Okay. Now here's what's important. I'm going to differentiate both sides with respect to time. So the derivative of a with respect to time would be dA over dt. The derivative of L squared would be 2 times L times the derivative of L with respect to time. And this is where I fill some things in. Look, I'm looking for this. I know this. And I know this. Okay, I can solve that no problem. dA over dt is 2 times 4 times 1.25. Okay, 2 times 4 is 8 times 1.25 is going to give me 10. Okay, now let's think about, let's put some units on this. It's area. Okay, it's the rate at which the area is increasing. So I know area is going to be in square units. In this case, it's meters. So I'd have meters squared. Okay, and it's per unit of time. Make sure the units of time match these units of time. So to answer that question, I would say the area of the square is increasing at a rate of 10 meters per second. It's important not to fill anything in until you have it differentiated with respect to time. You can only fill in the values that are changing, okay, after you differentiate with respect to time. If you have like a value that's not changing, well then it would be okay to fill it in up into this equation, and we'll talk about one of those in our next video when we talk about the ladder questions. All right, I'll show you what I mean by that. But find your equation that relates the quantities, differentiate both sides with respect to time, and then fill in your known quantities and solve for the unknown. Another problem. Suppose you tossed a stone into a lake. Circular ripple starts and moves outward with its radius increasing at a rate of 5 centimeters per second. All right, well, check this out. It's the radius increasing at a rate of 5 centimeters per second. That's not the radius. It's not r equals. Okay, that is, for my given information, I've got dr over dt as 5 centimeters per second. I know it's something over dt because there's a unit of time attached. Be mindful of your units. What if it said it was decreasing, not increasing? If it was decreasing, I put a negative there. And that's important too. If something is getting smaller, I always make sure it's a negative. Like if a distance is getting smaller, give it a negative. All right, it doesn't have to do with like left and right or up and down in this case. All right, it's the distance that's getting smaller. Make sure it's a negative. How fast is the area of the circle increasing? So dA over dt is what they're asking me to solve for. So I don't know. And then it says after 3 seconds. Okay, they do give me this time value of 3 seconds. Okay, well that's helpful for one reason, and I'll show you why. If you're wondering what formula relates the area of a circle, so it's a circular ripple, all right, to its radius, well that would just be the area of a circle, pi r squared. Okay, now watch when I differentiate with respect to time. dA over dt on this side, and here I get, now you can think of this as pi, that's a constant, times the derivative of r squared, well that would be 2r times dr over dt. Okay, and you could write that as the following. 2 pi r times dr over dt. Now check this out. Here's where the time is going to come into to help us. I know 2, I know pi, okay, but I don't have this. I do have dr over dt. That dr over dt, okay, would be 5. So I'd have 2 times 5 times 5, that's 10 pi times r. Well, I can figure out what r is, okay? How do I figure out what r is? Well, think about this. If the radius is increasing at 5 centimeters per second, okay, I'm going to take that rate and I'm going to multiply it by 3 seconds. Seconds would cancel, and I get a radius equal to 15 centimeters. All right, now think about that for a second. So your circle would look like this. At 1 second, the radius would be 5 centimeters. After 2 seconds, the radius is going to be 10 centimeters. And after 3 seconds, the radius is going to be 15. It's growing at a rate of 5 centimeters per second. All right, now I have this value here, and I can sub everything in, and I can solve dA over dt. And notice I wouldn't fill that 15 in here. Like I said, you can't, that number is changing. The radius is changing. So you can't fill those changing quantities in until you differentiate with respect to time. So at this point, now I can fill it in. That'll be 15, and that is a 5. So 15 for the radius, and 5 for the rate at which the radius is increasing. All right. A lot of textbook would just leave this as 150 pi. Okay, 2 times 15 is 30, times 5 is 150, times pi is 150 pi. All right, and units, remember it's the rate at which the area is increasing. So area would be in units squared, in this case centimeters squared. And per unit of time, I have to go with seconds. The unit of time would be the same as this unit of time. Okay. Now, if you wanted to write that as an exact value, that's pretty easy too. You would just take and multiply 150 times pi, and you get 471.24 as an approximate value. Both the same thing. I mean, this is nice. We don't need a calculator to figure that out. All right, you can just leave our answer as 150 pi centimeters squared per second. This down here probably makes a little more sense to most people. Okay, 471.24 centimeters squared per second. A lot of textbook might show this answer here. I'll accept either. Okay, a spherical balloon, a sphere. Okay, it's like a 3D ball, 3D circle. It's a ball. Okay, in this case, we're talking about a snowball. It's melting in such a way that its volume is decreasing at a rate of, okay, so our given information this time, look at the units, 1 cubic centimeter per minute. That's not a volume. It's the rate at which the volume is decreasing. So if it's decreasing, like we said on the previous slide, it should be a negative. Again, it's dV over dt because it's volume, cubic centimeters per minute with respect to time. At what rate is the radius of the snowball decreasing? So I want to know dr over dt at what rate. And it says, is it decreasing? So we know that this should be a negative, right? But we can work that out in a minute. If the original radius is 5 centimeters, they're telling me that r is 5 centimeters. Okay. what is the volume of a sphere? Here it is here. Now, I usually throw these up on the smartboard come test time, or I'll put it next to the question, but here it is. Okay. So, I am looking for dr over dt, and I'm given dv over dt and r. This is the formula that relates the radius of a sphere to its volume. I'm going to differentiate both sides with respect to time. Again, I don't want to fill the 5 in here right now because that quantity is changing. The radius, look at, that's what it's asking us to find. At what rate is the radius of the snowball decreasing? Well, I know the radius is changing, so don't fill it in yet. Don't fill those changing or those quantities in until after you derive. Now, 4/3 pi, that is just a constant. All right, so you can write down 4/3 pi, and you can multiply that by the derivative of r cubed with respect to time. The derivative of r cubed would be 3r squared times dr over dt. And I would clean this up. Watch. See you later. dv over dt is going to equal 4 pi r squared times dr dt. All right. Now, you can do that, like, instead of doing it, writing it like this, you could do the dv over dt, and 3 times 4/3, well, that'll give you 4 pi r squared times dr over dt. Okay, now I'm going to fill things in. I know that this dv over dt, that's -1 right here. It's going to equal 4 pi. I know the r value. R is 5. And I'll just work this out. 5 squared, that's 25, times 4 pi, that's 100 pi, times dr over dt. I'm going to divide both sides by 100 pi, and as an exact value, this would be my answer. Now, put some units on that. Okay? It's the rate at which the radius is decreasing, so notice it's a negative, that's good. And radius would be in linear units, so it's centimeters in this case, and it's per unit of time, centimeters per minute. As an approximate value, -1 divided by 100 pi, that's -0.00318 centimeters per minute. Just want to make sure I have those units of time correct. Okay, yeah. So there it is, full screen. One more question. Beach ball is being inflated so that its surface area is increasing at a rate of 100 centimeters per second. So I am given the area, or the dA over dt, the rate at which the area is increasing, 100 centimeters squared per second. Find the rate at which the radius is increasing, so I want to know dr over dt, and they tell me that r is 2. All right. Beach ball, what shape is that? She said sphere again. You are correct. Surface area of a sphere is 4 pi r squared. I'm going to differentiate both sides with respect to time. So this is going to be the constant 4 pi times the derivative of r squared. That'll be 2r times dr over dt. That's going to give me 8 pi r times dr over dt. And now it's time to go filling things in. This is 100 centimeters squared per second. My r value is 2 centimeters. And I'm looking for dr over dt. So this is 100 equal to 16 pi divide both sides by 16 pi, you'd get 100 over 16 pi. As an exact value, you could reduce that. Okay, divide them both by 4, 25 over 4 pi. And the units, linear units, so it's going to be centimeters. That's what the radius would be measured in. The unit of time in this question was seconds. Again, that is an acceptable answer. Okay, as an approximate value, 25 divided by 4 times pi. All right, if you do that, 25 divided by 4 pi, you get 1.99 centimeters per second. So for that beach ball, okay, the radius would be increasing at 1.9 centimeters per second if the area is increasing at 100 centimeters squared per second. And you're finding that rate at the instant the original radius is 2 centimeters. So remember, that value would be growing. As you pump more air into the beach ball, the ball is going to get bigger, so the radius is going to get bigger. All right, these are applications of derivatives. Okay, I'll have a little sheet for you to work on. You can try those. All right, I'll just scroll back through so you can see each one. All right, pause the video at any point if you want to see. Okay. And I want you to finish up your worksheet. So that is that.